All right, next up we have JJ Zanazzi from UC Berkeley.
Yeah, so thanks so much for the intro. So we're nearing the end of the day. We've heard a lot about different processes to stir up exoplanetary systems. We heard about highly eccentric planets, runaway gas accretion, like large tilts. So today what I'm going to do is I'm going to try and bring us all back down, a way to dynamically cool different types of exoplanetary systems. So Melina gave an excellent talk. She already introduced this plot. So the y-axis here shows this projected obliquity angle between the stellar spin axis and orbit normal projected onto the line of sight of the observer, Ross-Glafman effect. Y-axis here shows the effective temperature of the star. We're going to first look at are the hot Jupiter systems with obliquities colored in red, obliquities with host stars larger than 6100 Kelvin, this thing called the Kraft break. We see there's this big spread of obliquities, and this is actually what we expect for hot Jupiter systems, right? They're expected to form through highest interesting migration. You expect a big scrambling of these angles. Now what we're going to do is we're going to take a look at these blue points, right, below this Kraft break. And in sharp opposition to this big scramble of large inclinations, these ones all seem to be aligned. There's not really a reason why planet formation should operate very differently if you just change the effective temperature of the host star by a few hundred degrees Kelvin. Instead, what people have been really rallying around is this has something to do with the structure of the star. So stars below this Kraft break, they have these big convective envelopes. And this tidal forcing from the hot Jupiter is thought to interact with these big convective envelopes. And this dissipates energy, working to bring the star into alignment with the orbit normal of the hot Jupiter. I think it's fair to say, though, that these processes have proven a little bit problematic. So equilibrium tides engulfs the hot Jupiter before alignment, and inertial waves has really hard time realigning retrograde obliquities. So what this brought me to is a different process called resonance locking, which argues that you have these natural oscillations in the star that get resonantly excited by the companion, and it exerts a backreaction torque on the companion, which can accelerate the tidal evolution of the system. So that's what I'm going to talk about now, the physics of how this process operates. So the dashed line right here shows when the forcing frequency of the hot Jupiter exactly equals one of the natural oscillation frequencies of the star. We've heard a lot about the natural oscillation frequencies earlier in this conference. What the y-axis here shows is the dissipation rate, x-axis distance. So positive dissipation rate, of course, orbital energy is negative, inversely proportional distance. Positive dissipation means this orbit is going to move from over here inward, right? And so if we put the hot Jupiter over here, it's going to plod slowly along. It's going to move really quickly up here over this hump. It's going to move slowly again. So what we're going to do is we're going to think about what happens when we put the hot Jupiter really close to this exact resonance and just let the system evolve, right? So let's go ahead and do that. Hot Jupiter close to this resonance. Like I mentioned before, it's going to want to move away from this exact resonance. If nothing else is happening, what's going to happen is the hot Jupiter is just going to go to this trough. It's just going to plod along to whatever constant Q theory dictates its dissipation. And the next resonance is pretty far away. So this doesn't do much. But this isn't the only thing that's going on. So as the star evolves, hydrogen burns into helium, which causes the core to contract, which increases the core density and the Brunt-Väisälä frequency as well. And all this works to move these resonances inward just a little bit. It turns out there's a location where this hot Jupiter can resonantly lock onto the orbit. That's why this theory has this name, resonance locking. And once it locks on here, it then surfs this resonance on inward, right? So as the star evolves, it surfs this resonance, and this process can accelerate the tidal evolution of the system. OK, so this is how it works. It turns out there's a nice reason to expect that this is going to be more efficient for cool stars. The oscillations that get resonantly excited, they're gravity modes. I like to call them rubber duck frequencies. If you have a rubber duck in a bathtub, you pull it down, you let it go. It's going to bob up and down at characteristic frequency. That's this thing called N, the Brunt-Väisälä frequency. So both stars below and above the Kraft break, their cores contract. The difference is that gravity modes, they only propagate in the radiative regions of the star, where energy is transported through radiation. So cool stars, they have these radiative cores, and so as they contract, they feel this contraction very heavily. But stars above the Kraft break, even though their cores are contracting, these G modes, they live in the suburbs. They don't care about the core. And so if you go back here, remember, right? So the rate at which these G modes evolve, they're evolving a lot for these cool stars. The rate tells you how much energy is dissipating in the system. And that's the key difference between this theory, my theory I'm going to talk about, and my competitors. I'm arguing the radiative cores, not the convective envelopes. It's the cores that are driving all of this dissipation. So this is how this theory works. It's going to work much more efficiently for cool stars. What we're going to talk about now is what this does to the obliquity. This is the new technical aspect that I did in my work. So to understand how it affects the obliquity, we're going to first think about the geometry of one of these stellar oscillations. Then we're going to force it by the hot Jupiter, and then we're going to put these two ingredients together to figure out what it's going to do to the stellar spin axis. OK, so here's the oscillation we're going to be thinking about here. It's axisymmetric, so here's the spin axis, j hat star. If we peer down the spin axis, we're going to describe this as a spherical harmonic. It's just a circle moving in and out. So it's going to have azimuthal number of 0. So now let's force this thing with the hot Jupiter. So j hat orbit is the orbit normal of the hot Jupiter. Red here is radial force pushing in. Blue is radial force pushing out. When the orbit is aligned, we go march around the equator. Red cancels with blue. It doesn't get excited. But if the hot Jupiter is highly misaligned on the right, it's got a 90-degree angle. Look at here, everything is blue, so the oscillation is being pulled out. Another instance, it's all red, it's being pushed in. And so you get this excitation of this axisymmetric oscillation only when the hot Jupiter is misaligned. So this is how you excite this thing. Now let's figure out what it does to the spin, j hat star, right? So to do this, what we're going to work in a coordinate system where the spin axis is in the z direction. We're going to tilt the orbit normal in the xz plane. And what we're going to think about is how the location of the hot Jupiter's true location, which is a solid purple, is ahead of where the hot Jupiter exactly balances the oscillation. So it's a little bit ahead because the oscillation is dissipative. And to figure out what it does to the spin, what we want to do is we want to calculate the torque. So to calculate the torque, we want to look down the x-axis. We want to figure out how this hot Jupiter is going to cause j hat star to evolve, because we want to figure out when it moves in this direction, because that's going to tell you how it aligns. So let's go ahead and let's do that. All right, so we're looking down the x-axis now. Red, pointing in the direction of the oscillation bulge, right here. Blue is the tidal force felt by the tidal bulge. If you remember torques, it's just R cross F. So we got R, right? We got F. We got a torque. It's moving out of the projector screen. So if I'm the spin axis, I'm feeling a torque in this direction. What I want to do is I want to tilt out of the projector screen. And I'm going to work to align myself with the orbit normal. This is that one snapshot. We can let the hot Jupiter orbit. We see at every instance, right, R cross F is always positive. Torque always aligns. So this mechanism, we got two things now, right? We just showed this obliquity damps due to resonance locking. That's one ingredient. We discussed the other ingredient earlier. It works more efficiently for cool stars. So what we're going to do now is we're going to put these two ingredients together, and we're going to figure out what this does to the obliquity. OK. Blue curves here. On the left, obliquities for cool stars. Red curves, obliquities for hot stars. Cool stars, they damp rapidly, like we just mentioned. It's much more efficient to damp obliquities for cool stars due to resonance locking. Hot stars stay highly misaligned. So that's great. This process damps obliquities. But I mentioned equilibrium tides has this issue, right, where it eats the hot Jupiter before it realigns. Let's look at the right-hand panel. So we stop everything when the orbit is aligned for the hot Jupiter. So we see way before the hot Jupiters get anywhere close to the Roche radius, the orbit has aligned. And so resonance locking doesn't run into this problem of tidal engulfment before alignment. So this is one way to show the calculation. So we can do it a little bit more thoroughly. We can vary different masses for the hot Jupiter. We can let the star spin down. We can include the fact that we're observing, we can use the fact that we're observing the star at some finite age. We can include not just the axis symmetric oscillation, all the oscillations. We can put in everything and do a full population synthesis calculation. And the answer which we get, this is shown here. So solid squares, these are the observations. Open squares, these are the theory from this population synthesis calculation. So see hot stars, they stay highly misaligned, just like we see observationally. Cool stars, on the other hand, their obliquities have damped substantially due to this process. We do still have a little bit of an issue. We seem to have a number of systems with pretty high obliquities. It's not clear exactly how significant this is yet. But my collaborators and I were encouraged by this result. So to conclude, resonance locking seems to be a promising way to explain why in hot Jupiter systems, cool stars have lower obliquities. So I'll take any questions, have them.
Over on the left side, then we'll start all the way at the back and maybe walk our way down.
Hey, great talk, thanks. So if resonance locking is true, would you expect that there's some kind of pileup of like hot Jupiters at a particular orbital distance relative to the convective envelope depth?
Yeah, good question. So on the pileup, that's more sensitive to highest intensity migration. So the main explanation, right? So highest intensity migration predicts you have the pericenter at about the Roche radius. Once the orbit circularizes, that's about twice the Roche radius. I think Sam Yi is finding that that's roughly consistent with everything. Resonance locking is going to move these orbits inward a little bit. Sir Milholland's done some excellent work to show that the distribution of orbital periods is consistent with resonance locking. But it doesn't explain the pileup. That's more highest intensity migration. Yeah.
J.J. Hermes from Boston University. So quickly, this would predict that fully convective M-dwarfs might not show this effect. So would you advocate for trying to do REM on fully convective M-dwarfs to see if they don't have much of this? Excellent question. Yes. Yeah, so yeah, like if hot Jupiters around M-dwarfs form the same way as hot Jupiters around higher mass stars, it's a big if. Songhu's shown that like you might have more dynamically hot orbits for higher mass stars. But if they form the same way, this process will not work for M-dwarfs because they're fully convective. So specifically right around like 35,000 Kelvin, below there, this shouldn't work. So that would be a really interesting way to test this theory.
Travis Metcalf, WGRC. Really nice results. So the couple of cool stars systems with higher obliquities, your theory would predict that those are the youngest stars in your sample, maybe. Is that the case?
Yes, yeah. So this process takes time to realign everything. So resonance locking does predict a correlation with age. Yeah, so the cooler stars, which have high obliquities, should be younger. Yeah.
Thanks. Yeah, very interesting. If I understood correctly, the G modes that are doing this locking are in the core, right? So it means you need a radiative core, but that's not what the Kraft break is. The Kraft break is the radiative envelope. The radiative core starts even for just a bit more massive than the sun, right? Mm-hmm. So I'm a bit confused. Where is the break? Is it at the Kraft break, or is it at the break? Is it at the transition from a convective to radiative core, observationally?
Yeah, well, so we can see, right? So it's a little bit fuzzy, right? So you can see, so for the hot stars, there's this pileup here. This could be formation or this tidal damping. But you see, like right around 6100 Kelvin, depending on whether, like depending on your stellar model, it depends on the metallicity of the star, right? You get the core to develop at different times. But yeah, so right around 6100 to 6200 Kelvin, that's when you start to see this very different variation in obliquity.
Thank you.
Yeah.
All right, let's thank JJ again.